In many organizations, people wonder, why is this just-in-time thing not working? That's a tough question to answer, but the reasoning in almost every organization leads back to one thing: waste. Just-in-time cannot work when processes are riddled with waste. In fact, no strategy will be successful when the process is designed with ample amounts of waste in it. So, what can we do about this? One of the core ways that both service-based processes and manufacturing-based processes can eliminate waste is by changing your equipment or departmental layouts. Let's start by understanding the inherent waste that can be found in functional-based and operational-based layouts. In many organizations, departments and manufacturing equipment are grouped together in what is known as a functional layout. For example, all the engineers sit together, or all the CNC mills are placed in one area. Since most of these machines or people perform specific jobs or tasks, jobs are often processed in a batch or lot to avoid lengthy changeovers. For example, all of widget A is processed before moving on to widget B, or all the planning is completed without any understanding of how this may impact other parts of the value stream. As a result of this, batched production, many forms of waste are created. We will look at three. The first one we will look at is waiting as a result of batched production. When parts or information are produced in batches or lots, other parts must wait until the entire lot is complete. In other words, the first item in a lot cannot move on to the next step until the last item in the lot is complete, and that means other lots must sit in the queue. Another type of waste that comes from functional layouts is transportation or conveyance waste. In most production processes, operations or tasks require different pieces of equipment or skills. As such, parts being produced in a functional environment must be transported to different pieces of equipment to be completed. Likewise, information oftentimes must be transported to different departments before it can proceed. In every example of transportation, typically forklifts, conveyors, email, people, or other machines or forms of energy are required to move the products or information. None of these forms of transportation are value-added, as there is no transformation of the products or information during the transportation or conveyance. Finally, in most functional-based organizations, space is being wasted. Another form of inherent waste that occurs when functional layouts are used is wasted space. Functional layouts take up a great deal of space as well as introduce other types of waste due to the functional layout. Now, before we move on, we'd like to give you a little challenge. Think about the 8 forms of waste and functional layouts, and then answer this question: what other forms of waste might occur in a departmental design or a functional layout? You can write your answers down, comment, or answer in the upcoming assignment, and we'll see you in the next lecture. In the functional environments we've discussed before, workers stay at one machine. They complete the operation, then move the product or information along to the next operation. And, while this may make sense in a functional layout, we would need to continue to live with the inherent waste in functional environments. To fix this, organizations need to move towards process-based or flow-based environments. As you may have guessed, moving from a functional environment to a process-based environment changes the way people interact with machines or activities. Let's consider this interaction for a moment. In a process-based layout, different machines are placed together to enable flow. For simplicity, let's imagine a straight line of different machines that has an input and an output. This type of process-based layout would greatly reduce transportation, movement, and waiting in a process. And while these benefits are great, one challenge still exists. A company would not want to place one person at each machine in a process layout. Economically, this would not be practical. As such, employees need to be cross-trained to run various machines or complete different tasks. Cross-training people has many benefits in an organization. To start, employees are better able to handle a wide variety of challenges. They understand the entire value stream and they become more valuable to the company. Combined with automation, a cross-trained employee can really make a value stream flow. When employees understand the entire process, they can see how activities affect customers and suppliers much easier. In addition to this, many people begin to take a more deepened sense of pride in their work, which in turn allows them to take full responsibility for the work they do. One way that companies need to manage cross-training is with a visual skills matrix. The visual skills matrix gives employees a better view of who can do what and helps managers and supervisors set their teams up for success. Another change that often occurs when companies move from functional layouts to process-based layouts is the need for employees to move with the flow of the process. This often requires employees to be able to stand, which gives them the ability to move with the flow of their process or value stream. Standing when you are working will enable you to walk and move more freely. In addition to this, many employees find that the ability to stand in both manufacturing and service environments gives them a better ability to identify waste, find and root out problems, and is also highly beneficial to one's health. As you can see, cross-training in any organization is powerful for the company and for the people within the company, especially in a just-in-time environment. You've now learned how cross-training can help a company create more flow, and as always, we'd like to present you with a question that you can answer on paper, in the comments, or in the upcoming assignments section. Do people in your organization run multiple machines? And if not, what do you think would need to take place so that people could run more than one machine? Well, thanks for joining us here. Remember to review and answer questions as they come. They will help you gain a deeper understanding of what you are learning. We'll see you right back here soon on Lean Strategies International LLC. Many organizations begin the process of implementing flow by setting up equipment needed in the transformative process in a straight line layout. This is indeed much more effective than a functional environment and eliminates a great deal of the waste that come from the functional and departmentalized organizations. And while these straight line layouts are more effective than functional layouts, they do still have waste in them. One of the most obvious is that when a process is complete, the worker must walk all the way back to the beginning of the process and begin again. As you know, this introduces waste into the process as it adds no value to the product or service. So, how do we solve this? One of the most common ways that this problem in particular is solved is by implementing a U or C-shaped cell arrangement. In a cellular layout, your equipment is placed in a cellular layout that looks much like a curve, horseshoe, or the letter U or C. This not only gives the benefits of a straight line flow, but it also places the first and the last steps in the cell much closer together, which minimizes forms of waste. Cellular layouts are the optimal flow-based layout. A cell is a close arrangement or setup of people, machines, or workstations. The purpose of a cellular layout is to fulfill a processing sequence while simultaneously reducing wait times, transportation, and other forms of muda. In addition to removing various forms of waste, cells are very effective and promote and facilitate effective flow lines. Cells can be in many different shapes and attempt to spread work evenly amongst the resources. You now know what a cellular layout is and why so many people use cells to reduce waste. Now, before we go, consider the following question. If you placed your equipment in a cell, what improvements would you see? You can answer your question in the comments, upcoming assignment, or on a piece of paper at your desk. Thanks again for watching. And don't forget to come back often right here on Lean Strategies International LLC, where you can find solutions that ignite your power today. Have you ever had a situation where you desperately need a tool or equipment in a certain place, but what you have is in another place? If you have, then this module will help you understand why the just-in-time system seeks to make the switch to more flexible machinery. Let's jump in. In a traditional manufacturing environment, you want the biggest, baddest, fastest, and most reliable machines you can get. And you want this in just-in-time too. The difference is that equipment used in batch and lot production is generally different from equipment used in a just-in-time environment. For example, in many traditional organizations, desktops are set up for employees to use in their respective departments. These desktops, while helpful and much more efficient than paper and pencil, are not as flexible as a laptop or iPad is when an employee needs to go to the Gemba. Engineers, for example, frequently collect data and information. This could be much more efficient when information can be accessed right at the point of analysis from tools like a phone, iPad, or laptop rather than documenting information on paper and taking it back to your desk to enter into a system. Manufacturing environments, for example, may be able to use smaller machines, which gives them more ability to move items around, lower maintenance costs, and train more people to use the machines. When companies lower batch sizes, they not only improve quality and efficiency, they also use less space, which means they have more room for value-adding activities. Also, smaller machines that don't run for hours at a time, making lots of parts, are easier to monitor. One of the greatest benefits of smaller and more flexible machines is that strategies like total quality maintenance are much easier to implement, and maintenance costs are much, much lower. As you can see, flexible machines can benefit a company in many different ways. You don't always have to have the biggest, baddest, and fastest machine on the market. Just-in-time seeks to implement machines and tools that are just the right size, run at right speed, and are easy to maintain, as well as being flexible and mobile. Now, this may be a new concept for you, so let's challenge the idea of creating flexibility. Find a tool, machine, or piece of equipment you use daily, and then share in the comments, upcoming assignments, or on a piece of paper how you would make that tool, machine, or piece of equipment more flexible or mobile. We look forward to hearing back from you right here on Lean Strategies International LLC, where you can find solutions that ignite your power. What is intelligent automation in the just-in-time system? To put it simply, automation. Much of the equipment or machines that are used in the just-in-time system are built with automation. Automation, also referred to as jidoka, is the idea of making machines in such a way that they have intelligence of their own. This creates an environment where people do not have to stand and stare at machines or data. They can perform their tasks and other tasks rather than monitoring situations. Automation does not completely automate machines. It does, however, make them semi-automated. Frequently referred to as automation with a human touch, automation helps support the idea of flow in a process. Automation can detect abnormalities, signal when a machine starts and stops, count parts or information, and at times help control a process. Shigeo Shingo once referred to automation as pre-automation. This is because it separates workers from machines through mechanisms that detect abnormalities in a process. Dr. Shingo said, there are 23 stages between manual and fully automated work. To be fully automated, machines must be able to detect and correct their own problems, which in many cases may not be the best economic choice. Nonetheless, many organizations will automate information and equipment so that people can avoid dangerous, unbalanced, stressful, or repetitive conditions which add no value. When a worker is freed up from these conditions, they can then perform value-adding activities instead of simply monitoring a situation. There are 4 critical stages involved in jidoka. First, detect the abnormality. Next, contain or stop the abnormality. Then fix the abnormality. And finally, solve the root cause and ensure it does not happen again. These 4 critical stages or principles are also a vital part of an approach to error proofing known as poka-yoke. Poka-yoke is a Japanese term that means mistake proofing. Its purpose is to eliminate product defects by preventing, correcting, or drawing attention to errors as they occur. Now, you may be thinking, this automation sounds expensive, and in some cases it can be, but truthfully speaking, automation is often very simple and affordable. Many machines, software, or information systems can be modified to complete tasks in a semi-automatic way and free up workers from unnecessary repetitive tasks. This in turn gives operators the ability to operate multiple machines in a process or make improvements in other areas of an organization. Now that you have a general understanding of automation and how it can help people and organization, we'd like to leave you with a challenge to stretch your mind on the concept. Go for a Gemba walk in your organization. As you do, try to answer the following questions in the comments section, upcoming assignments section, or on a piece of paper. Do you see people in your place of work that simply monitor equipment? And, if you do, what exactly are they looking for? Do you feel that they could be doing something else that may add more value? We look forward to hearing your thoughts in this question, and we'll see you in the next module right here on Lean Strategies International LLC. Have you ever wondered, why does this problem always seem to appear again? Or, why doesn't this improvement seem to stick? In this module, we will look at one of the most important things you can do to make improvements stick: standard work. Standard work is a detailed definition of the current agreed-upon steps needed for a person to complete one work cycle in the absolute best and most reliable method possible. It goes without saying, but when improvements occur, it is important to standardize the improvements. Without new standards in place, it is very likely that the process will slip back into the way it's always been done before. In the just-in-time system, it is absolutely essential that you have standards in place. Taiichi Ono once shared, "Where there is no standard, there can be no Kaizen." This is true in the sense that improvements are only a figment of our imagination if we don't have somewhere to start or a baseline to measure from. As such, each process in a pull system depends on both the suppliers and customers in a process to deliver the right product at the right time and in the right amount. Without this, pull systems and the just-in-time system simply would not work. One way that a company can begin to establish standards and stable processes is to begin with standard work. Standard work makes it possible for processes to be measured, and it makes it much easier to improve upon. You may hear standard work referred to as standard operations or even work standards. Whatever the case, standard work has three main pieces in the standard work puzzle: tact time, standard sequences of work or standard work sequences, and standard in-process inventory or standard work in progress. Another important measurement to keep in mind once your tact time has been established is your cycle time. While this isn't a main piece of the standard work puzzle, you will at some point need to understand how your current cycle time compares to your tact time. We will introduce cycle time along with the other three pieces of the standard work puzzle in upcoming lectures. Now, before we go, let's stretch our minds again. You can answer the following questions in the comments section, upcoming assignments section, or on a piece of paper at your desk. What do you think? Do you agree with Taiichi Ono's statement? And why? We look forward to the discussions that may start and the interaction that's possible as you answer these questions. We'll see you in the next module. First, and arguably most important element of standard work is tact time. The purpose of tact time is to solve an age-old problem and match production with demand. It is often referred to as the heartbeat of a lean production system, and so it is also with standard work. Tact time refers to the rate at which products, information, and/or services need to be completed in to keep up with customer demand. Much like the pulse of a heart rate, tact time tells us whether we are beating at a healthy rate or we are falling dangerously behind. Tact time is a calculation that divides the available production time by the customer demand. Here's an example. If a factory operates for a standard 8-hour workday, or 480 minutes per day, and their customer demand is 240 parts per day, the tact time would be 2 minutes per part. As you can see, tact time attempts to match production with the required customer demand. Tact time is essential in setting standard work because it sets the pace that operations need to produce at in order to keep up with customer demand. This is different from cycle time. Cycle time is the amount of time it takes to complete an individual operation or task from start to finish. In other words, cycle time is the time required, and takt time is the demanded time. Another way of looking at it is that cycle time is your current state, and takt time is the goal. As you strip waste from a process and draw down your cycle times, the goal is to meet the customer's takt time. Here's an example. Let's say you establish some standard work, and the operator's current cycle time is 4 minutes, but your takt time is 2 minutes. We would need to review the process and look for ways to remove waste that may be slowing the process down and speed the process up. Now that you have an understanding of what takt time is, let's test our new knowledge out. Let's say you work at a factory and you work a standard 8-hour day, or 480 minutes. Your customer demand is 120 parts per day. What is your takt time? You can answer the question in the comments section, upcoming assignment section, or on a piece of paper at your desk. We look forward to hearing back from you, and we'll see you in the next module. Standard work is a detailed definition of the current agreed-upon steps needed for a person to complete one work cycle in the absolute best and most reliable method possible. It is made up of a few different elements, one of them being the element of standard work sequences. People cannot perform or achieve standard work without having a regular, standard work sequence. In this lecture, we will answer the question, what is a standard work sequence or work sequence? Work sequence is the order in which work is performed. The work sequence is generally made up of the best possible method of performing a task or producing a product. Work sequences should be established with the absolute minimum amount of waste in the sequence. A simple way to remember what a work sequence is that it is the order in which tasks are completed. You may hear a work sequence also called the sequence of operations. Many times a work sequence begins as a very logical sequence of steps. As time goes on, and through small and simple improvements that should occur, the work sequence should progress towards an ideal state. Let's look at an example of a work sequence. Let's say K&K cooks eggs for a customer. The work sequence is the steps necessary to make the eggs. It looks like this. First, you retrieve the raw materials. Next, you gather your tools. After that, you crack your eggs, then mix your ingredients. Cook, and finally enjoy your eggs. As you can see, these steps document a sequence for cooking eggs. Of course, this is a logical sequence and could have more detail and improvements added to it. Nonetheless, the work sequence can be repeatedly performed. A well-designed process will have materials and tools situated at or close to the point of use. It will also create an efficient flow of work. Documenting a standard work sequence or the steps needed helps ensure that times are consistent, quality is consistent, safety is present, and the end result is as consistent as possible. You now know what a work sequence is. Now, let's test our new knowledge by completing this challenge in the comments, upcoming assignments section, or on a piece of paper. Find a process you perform regularly and use a number format to write down your work sequence. Remember, we just want to see step 1, step 2, step 3, and so on. We look forward to seeing your work sequence here on Lean Strategies International LLC. Remember, by sharing your work sequence, someone may be able to help you make it better or help someone else improve. We look forward to seeing you back here in the next video. One-piece flow is not easy to achieve. In fact, it is very difficult to achieve. Nonetheless, it is the ideal form of flow for the just-in-time system. With that in mind, one must consider, what do I do if I have not yet reached one-piece flow? In this lecture, we will look at a very important piece of the standard work puzzle: standard work in progress inventory. Let's get started by first answering the question, what is standard work in process inventory? Standard work in process inventory is the minimum necessary level of items or materials needed to maintain the proper flow in a production environment. It would be impossible to create a standard work environment without understanding what the minimum amount of inventory you need on hand to keep the line flowing is. You would have bottlenecks, constraints, and issues all over. SWIP, or Standard Work in Process Inventory, is not the ideal. It essentially acts as a buffer of sorts so that the line can continue to flow if tact is not met or an issue pops up. The goal, of course, is to achieve true one-piece flow. But until then, SWIP will help keep the lines moving. Keep in mind that SWIP is calculated in many different ways, and while we won't dig into calculations just yet, you should note that if our work in process inventory is higher than our SWIP is set at, you will have excess inventory. If, on the other hand, you have less SWIP, then you will likely run out and bring work to a complete stop. With this in mind, we'd like to challenge you on this aspect of standard work by answering the following question in the comments section, upcoming assignments section, or on a piece of paper. At any given time, how much work in process inventory does your work area hold? We look forward to opening up this discussion with you all. And remember, this is just the surface of SWIP. In later lectures, we will dig into how it is calculated, when to add and subtract inventory, and how to progress towards one-piece flow. So, until then, keep on improving, and we will keep on giving you solutions that ignite your power. Cycle time is sometimes referred to as standard cycle time. Cycle time is the amount of time it takes to complete an individual operation or task from start to finish. In other words, the amount of time required to process one part. This includes processing time on a machine, any manual work that may be required, waiting, inspection, walking, and any other activities involved in processing the one part. Cycle time can be calculated with a stopwatch. In addition to calculating your cycle time with a stopwatch, one of the most common ways to calculate a cycle time is to clock the operations multiple times, for example, 3 to 5 times, and then use the average cycle time as your standard cycle time. So, how do you calculate your cycle time? Calculating cycle time is actually quite simple. First, you define your starting point. Then, at the starting point, you start your stopwatch. Finally, once the operation or task is complete, you would stop your stopwatch, and that's it. Another type of cycle time is process cycle time. This type of cycle time gives us the ability to determine whether or not a process is capable of producing the required quantity in the required time for the next downstream customer or process step. Keep in mind that each of the process steps is ultimately determined and controlled by the takt time. With this in mind, cycle time can sometimes produce quicker than actually needed. When a cycle time is quicker than it's actually needed, inventory builds up as well as many other forms of waste. If a cycle time is slower than the needed time, parts or information are not produced quick enough. This oftentimes will create bottlenecks, shortages, delays, and can even reveal other issues. Tools like Kanban and other process improvements can help an organization control the flow of production of materials and information. And that's it, cycle time. Now, before we go, let's test your new knowledge out. Go and get a glass and pour some water. What is the cycle time of you pouring your water? What was your starting point and what was your end point? You can write your answers on a piece of paper, comment in the comment section, or answer in the upcoming assignment section, and we'll see you in the next video. Many companies wonder, where should I start with my continuous improvement journey? And while the answer varies for everyone, in this module we will answer a key question that all organizations must consider. What is the foundation for continuously improving? Standard work is developed by people who actually do the work at the Gemba. They document the best known practices at the current time in an effort to set up conditions that allow them to improve later on. With that being said, standard work should never be the end of the improvement process. Rather, it is a starting point of the improvement process. Taiichi Ono once said it best when he coined the phrase, "Where there is no standard, there can be no Kaizen." This is true in the sense that only when standardization has occurred are we able to perform work the same way each time. When this occurs, we are better able to see the gap in what we are doing and what we would like to be doing. With this in mind, we all need to understand that standards are never the end. Rather, they are living documents that should be improved upon. So, much like a high jumper reaches a specific height and then inches the bar up, we should start with a standard and then inch our bar up again and again. With this analogy in mind, we can find the answer to the question, where should I start my continuous improvement from? Standardization is a good place to start. Once you have standards, the possibilities are endless. Now, let's end with a question that you can answer in the comments section, upcoming assignments, or on a piece of paper from your desk. In your current place of work, how are standards developed for processes and operations? And how are people able to access these standards? We look forward to the discussions that may develop from these questions, and we'll see you in the next video.